Hey, welcome back. In this section, we're going to produce a new way of handling non-homogeneous linear differential equations. Okay. In particular, we're just going to look at the first order and second order types. And the advantage of this method is that the function on the right side of your linear differential equation, like you see on the right, equation number 1 there, that f of x thing, we don't have to limit it to just be e to the x or sine x or x sine x or some sort of polynomial. Using this method, we'll be able to expand upon our sort of pool of possible differential equations we can solve, right? First, we're going to look at linear first order and kind of just do methods that we already know work. And then we'll introduce the variation of parameters and show it's basically going to give you the same answer. Okay, so anyways, first we'll do integrating factors. Comparing and contrasting homogeneous with the non-homogeneous, we're going to be able to pick out the complementary part of the solution and the particular parts. So here's the homogeneous version, here's the non-homogeneous version. Okay, so integrating factor, we're going to just leave it abstract, so use e to the integral of p of x dx. Multiply through by mu, collapse the left side, you get the derivative with respect to x of y times e to the integral of p of x dx. On the right side, you just get 0. Integrate both sides with respect to x, you get y, e to the integral of p of x dx equals c. And then divide both sides by e to the integral of p of x dx. C to the e to the negative integral of p of x dx. Okay, so that's the kind of the complementary part of the solution. Let's look at what we get from the homogeneous version. It's kind of the same, you know, just this, I'll put dot, dot, dot to imply that it's the same step as the steps to the, well, not really though, right? It's a little bit different. I might as well write it out. I apologize. So, you know, here's our mu, e to the integral p of x dx. This is really the only part that's exactly the same. Multiply through on the left again, you're collapsing. I mean, that part's the same. So you get y e to the integral of p of x dx. But on the right, you have to multiply by that e to the integral of p of x dx. And then you have f of x. Then you can integrate both sides with respect to x. So you get y e to the integral of p of x dx. Over here, we'll just tack on a constant. So e to the integral of p of x dx times f of x dx, and then plus some sort of constant will be floating around. And then I'm just going to divide everything by e to the integral of p of x dx. So I get y equals basically c e to the negative integral of p of x dx, and then plus this other guy, so that would be e to the negative integral p of x dx times the integral of e to, sorry, it just is what it is, you know. And then we have the f of x dx. So comparing the homogeneous version to the non-homogeneous version, you can see that this thing is our complementary part, and then this is the particular part. Okay. What we're going to do then is use the variation of parameters to produce this particular part. It's kind of what we're after, because I mean, ultimately, you can always solve the homogeneous version. Okay, it's that it's like getting that particular solution when you don't have those nice functions on the right side. That's the troublemaker. Okay, so we'll use this method called variation of parameters. Variation of parameters. I don't know the history of this method, but the book does say it's I think it's a astronomer Lagrange is the guy that sort of figured it out. But anyways, first we note that we already have kind of the solution to the homogeneous version here, right? So we'll say y1 equals, and instead of putting a constant in front, so the complementary part, we're going to just use e to the negative integral of p of x dx. So this thing is a solution to the homogeneous version, dy over dx plus p of xy equals 0. You know, if you plug that in, then you're going to see that it works. And so let's do that just for the sake of teaching something here. So I'm going to plop that into here. And what do I get? So the derivative of that thing is, you know, for any exponential, you just get the exponential right back, but then you have to take the derivative of the exponent. Okay, the derivative of that exponent, the derivative and the integral kind of cancel each other out, so you just get negative p of x. Okay, so I'm going to put that in front, negative p of x. So I'm noting this fact. And then plus p of x times this y e to the negative integral of p of x dx. And you see they're additive opposites, so it'll just equal 0. So it does fulfill the homogeneous equation. What we want then, okay, so we want then a solution of L of y equals f of x. Okay? And what we're going to do is make our particular solution y sub p equal to some function. Instead of using a constant, use some function of x, we'll call it u1 times y1. Okay? Okay, so note what happens if I plug that thing into my differential equation. I'll have the derivative with respect to x of u1 y1 plus p of x times u1 y1 equals f of x. Taking the derivative of that product, I've got to do a product rule. So I'll have, leaving u1 alone first, u1 times the derivative with respect to x of y1, plus leave y1 alone and take the derivative with respect to x of u1, and then plus p of x u1 y1, that equals f of x. Okay? And then this crucial kind of observation is important. If you take this part and this part together and then factor out the u1, what do we get? Well, we'll have u1 times the derivative with respect to x of y1 plus p of x y1, and then plus the y1 times the derivative with respect to x of u1, and that equals f of x. This then, we've already shown above here, is equal to 0, right? Because that y1 thing is just the e to the negative integral p of x dx, which we plugged into that thing and shown that was equal to 0. So we can get rid of that part and just have y1 derivative with respect to x of u1 equaling f of x. And then we could solve this as a differential equation, right? So we would have, after sort of separating, du1 with respect to x equals f of x all over y1. Separate some more, so we have du1 equals f of x all over y1 dx, and then we can integrate both sides and solve for u1, right? So u1 will be f of x all over y1 dx, and so our final answer for the particular solution yp remember, we presumed that yp right here is equal to u1 times y1. Okay, so u1 times y1. I'm going to put y1 first, so I have y1 times u1. u1 is f of x all over y1 dx, and then do substitutions for y1. So I have e to the negative integral of p of x dx times the integral of e then to the positive integral of p of x dx times f of x dx. And then if you look back up here, that is our y sub p, our particular solution. So this method was able to produce that particular solution, and that kind of hopefully verifies it in your brain as something that works. Okay? So let's move up to second order linear differential equations. Once you get the second order, it becomes a little more complicated to solve for u1. Because it's not just u1 you're solving for, there's a u1, u2, right? Because this was a first order, so you knew the form of the general solution of the associated homogeneous differential equation. That guy just has one function in its general solution. So we were able to kind of pick out a particular solution just by multiplying that one function by this u1. But now our general solutions for second order linear will have two parts to it. And so y1, y2, so we'll need a u1, u2, and the result is kind of a system of equations, and so we're forced into linear algebra, the linear algebra universe, okay? So anyway, second order linear differential equation, we want this form y double prime plus p of x, y prime plus q of x, y equals f of x. Then we'll know the homogeneous solution, the complementary part, that will be c1y1 plus c2y2. So what do we want for our particular solution? We're going to say u1 y1 plus u2 y2. Okay? I'm not going to go through the kind of tedious exploration here. I think it's a bit confusing. If you look down at linear second order, where are you? Yeah, down here. The algebra is a bit tedious. I'm just going to give you the long story short. So basically what you're going to do is sub that expression y sub p into the non-homogeneous equation, okay? And after you do that, so after subbing y sub p into our non-homogeneous differential equation, L of y equals f of x, and doing some algebra, some fancy footwork there. I think we have to make an assumption right here, and that becomes part of our kind of system of equations. So after doing some algebra, we are left with the following system. Which we have to solve for our u1 and u2. Okay, so the system is y1 u1 prime plus y2 u2 prime equals 0. And then the other equation, y1 prime u1 prime plus y2 prime u2 prime equals f of x. Okay? So that puts us in the land of linear algebra. If you're not taking linear algebra, basically you could use linear algebra to solve systems of equations. I'm sure you've solved systems of like equations of lines, 2x plus y equals 3, 3x minus y equals 5, things like this. Use the substitution method or the addition method. Well, the truth is you can transfer these into matrices. So 2, 3, 1, negative 1, 3, 5. And then if you take linear algebra, they teach you all kinds of methods for solving these things. Okay? One of the methods is Cramer's rule, which is used to solve this system right here. And at the end of the day, long story short, ultimately, we have the following equations differential equations, which must be solved. So for U1, we solve this U1 prime equals 0. And I would give you these formulas. I wouldn't expect you to have these memorized. Okay, all over the Wronskian. I've had teachers that forced me to memorize this, but no. So the top is a determinant operation. The bottom is the Wronskian. What this turns into, if you go on the diagonals, 0 times y2 prime is just 0, and then minus y2 f of x all over the Wronskian. And then to get u2, you just solve this next equation. So similarly, you'll have like a determinant on the top, but ultimately, if you do the determinant, you'll just get y1 f of x. So I'll just cut to the chase. All over W, okay? And if you solve those two differential equations, you'll get your U1, U2, and you're kind of done, okay? So there's a lot of details in there, but you kind of just, it's algebra and then systems of equations. You can imagine Lagrange coming up with this method. He was probably very frustrated with everything going on. It's just like, oh, I got to find a different way to do this, Anyways, let's go to the homework exercises. I don't think I put a lot of these in the homework, but let's take a look anyways. They can be nasty if the determinant is nasty and the Wronskian is nasty, but most of them are pretty doable. 4-6, I think. 4-6. You can see the answers are kind of nasty, but anyways, let's take a look at number 1. So we have y double prime plus y equals cosecant x. When I'm going through my homework, I have these two formulas, basically. So let me change this a little bit, and I'm going to copy this guy, so I have to redraw them. Move them over here, and then I'm going to go down to snippet and take a picture. Out of the way, please. And I don't want that stupid box in there. And I accidentally closed out the program. So let's go back here. So as I do my homework, I have these two formulas in front of me. Save as variation the parameters. Let's go up to your class. 2021, 2510. I'll put that in there. But I'm just going to put this to the side so I have it as I go through and do my homework, right? Okay. So first you need the complementary part of the solution. And so you have your characteristic equation, m squared plus 1 equals 0. So here m is plus or minus I. So our complementary part of the solution is going to be c1 cosine x plus c2 sine x. And then this guy here is your y1. This guy here is your y2. And this guy right here is your f of x. Okay. Okay, so what do I need? I need a Wronskian. So the Wronskian, what do we have then? Cosine x, sine x. I just take y1 and y2, and then down the column take the derivative, right? So negative sine x, cosine x. It'll be cosine times cosine, which is cosine squared x, minus negative sine times positive sine is negative sine squared x, but negative negative becomes positive. So they're real nice to you this time. The Wronskian is just 1. Okay. So my first differential equation, y1 prime is equal to negative y2, so negative sine x, times f of x, which is cosecant x, all over the Wronskian, which is 1. Okay. So let's simplify it first before we get carried away. Cosecant is just 1 over sine, so this will just be negative 1. And so integrating both sides with respect to x, I should get u1 equals negative x. So yeah, u1 is negative x, and then I need to get u2. So let's put u2 over here. So u2 prime is y1, which is cosine x, times cosecant x, all over 1. Simplifying this a little bit, that'll be cosine over sine, which is cotan x, and then I want to integrate both of those. So u2, the integral of cotan, if you've forgotten, is negative ln absolute value cotan. Whoops, it's sine. So this, I always mess this one up with cosecant. Sorry. So it's just plain old ln of sine. If you do a u sub, turn cotan into cosine over sine, do a u sub on sine, and you'll get this guy. Okay. I don't need the constants on these guys. Finally, then my solution is going to be the complementary part. So c1 cosine x plus c2 sine x plus the particular parts, which are just the u1 times y1. Okay, so the first one, negative x times cosine x. And then the second guy is u2 times y2. So again, y1, y2 are from the complementary part of the solution above. So I have sine x ln absolute value of sine x, which looks weird, but I believe that's it. Yeah. Okay. So not too bad. Let's look at number 4, which looks kind of annoying. We have y double prime minus y is cosh of x. So in this case, I'm going to rewrite cosh just to make my life a little bit easier. Maybe that'll be easier. Maybe not. Well, let me think about it. Okay. So anyways, first off, get the homogeneous, the complementary part of your solution. So you need your characteristic equation. So it'd be m squared minus 1 is 0. So m is going to be plus or minus 1. And then your particular solution, your complementary part is going to be c1 e to the negative x plus c2 e to the positive x. Going to need that Wronskian from that thing, so the Wronskian. Yeah, so I think the reason why I want to convert this to exponentials is because if not, I'm going to have this weird mixture of coshes and cinches, and this might just be easier to just say forget it and write everything in terms of exponentials. So if you remember the definition for cosh, e to the x plus e to the negative x all over 2. Okie dokie. So anyways, get your Wronskian. So I have e to the negative x, e to the x, and then the derivative e to the negative x is negative e to the negative x. Derivative e to the x is just e to the x. On the diagonal, e to the negative x times e to the x is just 1, minus the other diagonal is negative 1, so I'm going to get 2 from my Wronskian. Then u1 prime, where's my formulas? u1 prime is negative y2. Okay, so again, this guy here is y1, this guy here is y2, and then this guy up here is my f of x. All right, so y2 is just plain old e to the x, and then f of x is e to the x plus e to the negative x all over 2, and then it's all over the Wronskian of 2. Rewriting that, distributing this guy, the constant will be 1/4. Anyways, pull 1/4 out, and then I have negative e to the 2x minus, I guess, just 1. E to the x times e to the negative x, add the exponents, x minus x is 0, so e to the 0 is 1. Okay, then I can integrate here, and I get u1 equals 1/4 times negative e to the 2x all over 2 minus x, and distributing the 1/4 if you wish, negative e to the 2x all over 8 minus x over 4. Then u2 prime is y1, so e to the negative x times f of x, which is e to the x plus e to the negative x over 2, all over the Wronskian of 2. So again, you're going to get something like 1/4 times, if you distribute e to the negative x, you get 1, and then plus e to the negative 2x. Okay. Integrating both sides, you get u2 is 1/4. Then, so the integral of this part would be x minus e to the negative 2x over 2, and then distributing, if you wish, x over 4 minus e to the negative 2x all over 8. So our final solution, y is equal to the complementary part, c1 e to the negative x plus c2 e to the positive x, and then plus y1 times u1. So we have e to the negative x times negative e to the 2x over 8 minus x over 4 plus y2 times u2. Y2 is e to the x, u2 is x over 4 minus e to the negative 2x over 8. Distributing to make it look pretty, you get y is c1 e to the negative x plus c2 e to the positive x minus e to the just plain old x. Just trying to write a negative x new all over 8 minus x e to the negative x over 4 plus x e to the x over 4 minus e to the negative x all over 8. Okay. Make sure there's no common terms, and hope, cross your fingers for good luck as you plug it into your system. And just making sure it's right. Yeah. Okay. I don't know. Some of them are, they are what they are, really. I'll do one more and then I'll cut you loose. So I do number 6. I double prime plus 3y prime plus 2y equals 1 all over 7 plus e to the x. Okay, get the characteristic m squared plus 3m, plus 2 equals 0. So m plus 2 times m plus 1 is 0. So negative 2, negative 1, so y complementary is c1 e to the negative 2x plus c2 e to the negative x. And what else? Need the Wronskian. So the Wronskian is going to be e to the negative 2x, and then e to the negative x. Taking derivatives, I get negative 2e to the negative 2x, and then negative e to the negative x. That's the diagonals. Then I get negative e to the negative 3x minus negative, so plus 2e to the negative 3x, which will equal e to the negative 3x. So that'll be a negative 3x. And then, what do I need? I need my formulas. Okay, so u1 prime is going to equal negative y2, so negative e to the negative x times f of x, 1 all over 7 plus e to the x, all over the Wronskian, e to the negative 3x. Okay. So this is equal to negative e to the positive 2x when I simplify these two, okay, and then all over the 7 plus e to the x. I'm going to integrate that guy. That doesn't look like a lot of fun, but we'll try anyways. I'm thinking of doing long division, believe it or not. So you have e to the 2x divided by e to the x plus 7. So you can multiply e to the x, will give you e to the 2x plus 7 e to the x, and then you subtract like this, and you get minus 7 e to the x. Okay. So you can rebuild your integral now as the integral of e to the x, and there's a negative in front, so it's a good idea not to forget that. So let's rewrite it as, after distributing the negative, positive 7 e to the x all over e to the x plus 7 minus e to the x, okay, dx. The first integral then, after containing my work here, the first integral, you could do a u sub on the denominator, so e to the x plus 7, and then du will just be e to the x dx, and then dx will be du over e to the x. Okay. So this integral on the right side here is going to become the integral of 7 e to the x over u times du over e to the x, and then minus the integral of e to the x, which will just be e to the x. Simplifying a little bit here, I get 7 times du over u minus this e to the x term. So basically I'm getting u1 equaling 7 ln absolute value of u, which is e to the x plus 7, and then minus e to the x. Okay, so there's my first part. Whoops, u1, just u1, not the prime. Then I need to get u2, so u2 prime is y1, which is e to the negative 2x. E to the negative 2x. Then f of x, which is 1 all over 7 plus e to the x, all over the Wronskian, which is e to the negative 3x. Okay. Simplifying here with this part, that will just be e to the x. So e to the x times 1 over 7 plus e to the x is e to the x all over 7 plus e to the x. And integrate both sides. Again, I've kind of already done this integral above. It's just the ln of e to the x plus 7. So I get u2 equals ln of the absolute value of 7 plus e to the x. Okay. I don't think I missed any constants. I wonder where that 7 came from over here. Well, that's from the long division. Okay, so that's the way it is. So finally, then I get my solution, y equals u1. Oh, whoops, sorry, the complementary part. So I need c1 e to the negative 2x plus c2 e to the negative x, and then plus u1 y1. So that would be 7 distributing. I'm going to distribute it. 7e to the negative 2x ln absolute value of e to the x plus 7 minus e to the x times e to the negative 2x is e to the negative x, and then plus y2 times u2, which is e to the negative x times the ln of the absolute value of 7 plus e to the x. Did I get it? Sure looks like it. Okay, great. So there it is in all of its glory. Yeah. So mainly just a procedural thing once you get through the theory. We'll leave it at that, and thank you for watching, and I will see you next time.